Our universe is unimaginably vast, but it might be just a single page in an infinite cosmic library. What if everything you see, from the stars to yourself, is merely one version of reality among countless others? We are about to explore 30 theories about the universe's hidden universes, a journey that will permanently stretch your perception of everything that exists. By the end, you will possess a mental map of the most radical frontiers of cosmology, from parallel worlds where your double lives a different life, to universes built from pure mathematics or existing inside a black hole. We will investigate if our cosmos is a hologram, a simulation, or one bubble in a frothing sea of eternal inflation. The answers are stranger than any fiction. What single idea about reality are you most eager to question? The cosmos we can see, stretching for billions of light years in every direction, feels impossibly large. Yet, the first and perhaps most staggering theory of hidden universes suggests it is nothing more than our local neighborhood. This is the Level 1 multiverse. It begins with a simple, profound question. What lies beyond the edge of our observable universe? Our telescopes have a limit, a horizon defined by the age of the universe and the speed of light. We cannot see beyond it, but most leading cosmological models suggest that the universe does not simply stop there. Instead, space itself continues, stretching out into a true, perhaps infinite, expanse. If that is the case, then our entire observable cosmos, with all its hundreds of billions of galaxies, is just one bubble in an endless, frothing sea. This idea flows directly from the theory of cosmic inflation, a period of unimaginably rapid expansion in the universe's first moments. Inflation may have stretched a tiny patch of space into a vast, smooth, and flat region, which became our universe. But if inflation can happen once, why not eternally? In an eternally inflating cosmos, new universe bubbles are constantly budding off, forever expanding into a greater meta-universe. Within our specific bubble, the laws of physics and the arrangement of matter are one possible outcome. But in an infinite landscape, every possible arrangement that can exist must exist. Think of shuffling a deck of cards. If you shuffle enough times, you will eventually get the same order twice. Now, imagine the universe is like a deck with an almost infinite number of cards, atoms, and particles. In a truly infinite space, the deck gets reshuffled over and over. Somewhere far beyond our cosmic horizon, the exact same sequence of particles that makes up our solar system, our planet, and you has been dealt again. There is another Earth with another version of you, reading these very words. In another region, a nearly identical Earth exists, but where you made a different choice this morning. Further out, Earths exist where history unfolded without a single dinosaur extinction, or where life never formed at all. This is not science fiction, but a logical consequence of infinity and the cosmological principle, the idea that on the largest scales, the universe is uniform. If the cosmos is infinite and roughly the same everywhere, then patterns must inevitably repeat. The sheer scale is humbling. Your life, with all its unique joys and struggles, is not just happening here. It is happening an infinite number of times, in an infinite number of places. This theory forces us to confront a radical idea. We are not just individuals, but statistical certainties. But infinity is not the only path to parallel worlds. A far more intimate and immediate kind of multiverse might be unfolding with every single decision you make. This is the many worlds interpretation of quantum mechanics, a theory born not from telescopes, but from the bizarre rules governing the smallest particles in existence. At the heart of quantum mechanics lies a profound mystery called the measurement problem. In the quantum world, particles like electrons do not have definite properties until we look at them. An electron can be in a state of superposition, meaning it is spinning both up and down at the same time, or existing in multiple places simultaneously. It is only when a scientist makes a measurement that this fuzzy cloud of possibilities seems to collapse into a single, definite outcome. For decades, this wave function collapse was treated as a fundamental, if puzzling, rule. But in 1957, a young physicist named Hugh Everett proposed a radical alternative. He suggested the wave function never collapses at all. Instead, every single possible outcome of a quantum event actually happens, but each one plays out in a newly created, parallel branch of reality. Think of the famous thought experiment of Schrödinger's cat. In the classic version, a cat in a box is both alive and dead until someone opens the box to look, forcing a single reality. In Everett's many worlds, there is no single outcome. The moment the quantum event inside the box is triggered, the universe splits. In one branch, the cat is alive, and the observer opens the box to find a healthy, if confused, pet. In the other, completely separate branch, the cat is dead, and a different version of the observer sees that tragic result. Both realities are equally real, they just can no longer interact with each other. This branching happens constantly at every quantum juncture. Every time an electron could go left or right, the universe splits so it does both. Every time you face a choice, even a trivial one like whether to turn left or right on your walk, the quantum processes in your brain that lead to that decision are also splitting reality. In one world, you turn left and see a beautiful sunset. In another, you turn right and find a lost wallet. The you in each world experiences only one outcome, believing it to be the only reality, unaware of the countless other versions of yourself living out the roads not taken. This theory elegantly removes the need for a special collapse rule, treating the entire universe with the same quantum mechanics that governs particles. It paints a cosmos of unimaginable fecundity, where every possibility is realized, where every life is lived in every conceivable way across an ever-expanding tree of alternate histories. The implications are deeply personal. It means somewhere, a version of you is living your greatest dream, another is living your deepest fear, and an infinite number are living variations you could never conceive. The universe is not just out there, it is branching from within you with every thought and every heartbeat. The branching of many worlds suggests a cosmos that endlessly divides from within. Yet there is another, even more expansive vision of creation, one where entire universes are born not from our choices, but from the very fabric of space-time itself. This is the bubble universe theory, a direct consequence of the concept known as eternal inflation. To understand it, we must journey back to the first fleeting moments after the Big Bang. Most cosmologists believe the infant universe underwent a period of hyper-fast expansion called inflation, where space itself stretched faster than the speed of light, smoothing and flattening our cosmic region. But what if inflation, for most of the meta-universe, never truly stopped? Imagine a vast, seething ocean of pure, unstable energy. This is the inflattened field, the engine of cosmic expansion. In most of this primordial sea, inflation rages on eternally, stretching space to impossible scales. But here and there, like bubbles spontaneously forming in a pot of boiling water, tiny pockets of this energetic field calm down. In these regions, inflation locally ends. the tremendous energy of the inflattened field is released, flooding that bubble with matter and radiation, and igniting a hot Big Bang. That bubble becomes an entire universe like our own, embedded within the eternally inflating background. Our entire cosmos, with all its galaxies and stars, is just one such bubble. And we are not alone. The eternally inflating sea is a cosmic froth, a foam of spacetime where new bubbles are constantly nucleating, expanding, and sometimes even colliding with one another. Each of these bubbles is a separate, self-contained universe, potentially with its own unique properties. This is where the theory becomes truly mind-bending. When a bubble universe forms and its local inflation ends, the fundamental constants and laws of physics within it can freeze into place. The strength of gravity, the mass of an electron, the number of spatial dimensions, all could be different from bubble to bubble. In our bubble, the laws allowed for the formation of atoms, stars, planets, and life. But in another bubble, the constants might be so different that matter instantly collapses or flies apart, creating a cosmos of pure, sterile light. Another bubble might have stronger nuclear forces, where stars burn out in a cosmic blink. Another might have extra dimensions of space curled up in strange ways. We are living in a universe with a winning lottery ticket, a set of physical laws just right for complexity to arise. The bubble multiverse offers a staggering explanation for this fine-tuning. With an infinite number of bubbles, every possible set of laws will exist somewhere. We do not observe our particular laws because they are special or necessary. We observe them simply because they are the ones that allowed observers like us to exist. This is the anthropic principle in a vast cosmic landscape. The scale is almost impossible to grasp. The space between these bubble universes is still undergoing eternal inflation, expanding so rapidly that the bubbles are forever driven apart, isolated islands in an ever-widening sea. We are, in a very real sense, trapped in our own cosmic bubble, unable to ever see or reach another, yet their existence would rewrite the story of our origins. The Big Bang was not the absolute beginning of everything, but merely a local phase transition within an eternal and infinitely creative meta-cosmos. The bubble multiverse paints a picture of isolated cosmic islands, forever drifting apart. But what if the hidden universes are not distant bubbles, but are instead hovering right next to us, separated by a gap thinner than a sheet of paper? This is the startling vision of the brane multiverse, emerging from the depths of string theory. To grasp it, we must first stretch our minds beyond the familiar three dimensions of space. String theory, a leading candidate for a theory of everything, proposes that the fundamental particles of the universe are not points, but unimaginably tiny, vibrating loops of energy or strings. For the math of string theory to work, it requires more dimensions than the three we experience. Most versions posit 10 or 11 dimensions of space-time. So where are these extra dimensions? The brane multiverse offers a compelling answer. They are all around us, but curled up or hidden in a way our senses cannot perceive. In this model, our entire three-dimensional universe is not an island in space, but a membrane, or brane for short, floating within a higher dimensional arena called the bulk. Think of our universe as a single page in a gigantic, multidimensional book. We are flatlanders living entirely on that page, able to move left, right, forward, and back, but utterly unaware of the stack of other pages above and below us. Those other pages are other branes, other entire universes, each with their own three-dimensional reality, floating parallel to ours in the higher dimensional bulk. The most astonishing part is their proximity. In some models, another brane universe could be literally a millimeter away from us in a higher spatial direction we cannot point to or move into. All the forces and particles we know of, like light and matter, are stuck to our brain, like ink soaked into a page. They cannot leap off into the bulk, which is why we cannot see or touch a neighboring universe, even if it's right next door. There is one cosmic force, however, that might be able to traverse this gap: gravity. Some theories suggest gravity, unlike other forces, is not confined to a brane. It can leak out into the bulk, spreading its influence between universes. This could explain why gravity is so astonishingly weak compared to other fundamental forces. Its strength is not feeble. It is simply diluted because it spreads out into extra dimensions we do not see. This idea leads to a truly cataclysmic possibility: brane collisions. If two of these vast, floating membranes were to drift through the bulk and smash into each other, the energy released would be beyond comprehension. Some physicists, like those behind the ekpyrotic universe model, propose that our own Big Bang was not a singular eruption from nothing, but the aftermath of just such a collision between two branes. The immense heat and density of that impact reset our cosmic clock and ignited the expansion we see today. And if it happened once, it could happen again. In the silent, higher dimensional bulk, another brane could be on a slow motion collision course with our own, a cosmic destiny waiting to unfold across an unseen axis of reality. The silent collision of branes offers one answer to our cosmic origin, but it also hints at a far grander destiny, a universe destined not for a cold end, but for an eternal rebirth. This is the theory of the cyclic universe, specifically the ekpyrotic model, which transforms the single dramatic event of the Big Bang into a mere chapter in an endless, pulsing story. In this vision, the cosmos has no true beginning and no final end. Instead, it undergoes an infinite series of cycles, each one starting with a fiery collision and expansion, and ending with a slow, gathering contraction, leading inevitably to the next colossal impact. This stands in stark contrast to the prevailing forecast for our universe's fate, known as the heat death. Based on current observations of accelerating expansion, the heat death scenario paints a lonely, fading future. Over trillions of years, stars will burn out, galaxies will drift apart into darkness, and all usable energy will dissipate into a vast, cold, and uniform void. It is an ultimate and permanent stillness. The cyclic model rejects this finality. Instead of a one-way slide into entropy, it proposes that the universe itself possesses a built-in reset button, triggered by the hidden dimensions of the brane multiverse. Here is how the cycle might unfold. Our current universe, expanding from its last brane collision, will eventually slow its growth. The mysterious dark energy that now drives galaxies apart could gradually transform, becoming an attractive force. Over scales of time that dwarf the current age of the cosmos, the expansion would halt, then reverse. Distant galaxies would begin to rush back together, space itself contracting, heating the universe into a fiery soup. All structure, from galaxy clusters to atoms, would be obliterated in a cataclysmic convergence known as the Big Crunch. But this is not the end. As our three-dimensional brane contracts, it is moving through the higher dimensional bulk on a collision course with a neighboring brane. The Big Crunch becomes the prelude to a new Big Bang, as the unimaginable energy of the collision floods our brane once more, restarting the cosmic clock and launching a new epoch of expansion. With each rebirth, the slate is not merely wiped clean, it is potentially rewritten. The violent physics of the collision could scramble the fundamental constants that govern reality. In one cycle, gravity might be stronger, creating a universe of tiny, hyper-dense stars that burn out in a flash. In another, the nuclear forces could be weaker, preventing atoms from ever forming complex structures. Our cycle, with its just right laws for life, is simply one fortunate roll of the cosmic dice in an endless series of throws. This means the history of the cosmos is layered, like rings in a tree trunk. Our universe's 13.8 billion year history is just the current growth ring. Before it lies a hidden archaeology of previous cosmic epochs, each lasting perhaps trillions of years, each with its own unique physics and potentially its own forms of unimaginable complexity. All evidence of those prior universes, however, was likely scoured away in the fiery reset of the last collision, leaving us with a cosmic amnesia, staring up at a night sky that whispers of only one beginning. The endless cosmic cycles suggest a universe of immense depth and scale. Yet one of the most profound theories of hidden reality argues the opposite, that our rich three-dimensional experience is nothing but a magnificent illusion. This is the holographic principle, a concept so radical it proposes our universe, in all its complexity, is a hologram, not a flickering light show, but a cosmic projection, where all the information describing every star, planet, and thought is actually encoded on a distant, two-dimensional surface. The origins of this astonishing idea are not found in philosophy, but in the fiery paradoxes of black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery: black holes have entropy, a measure of disorder or information content. Stephen Hawking later showed they also have temperature and can slowly evaporate. This created a crisis. If a black hole swallows an object, like a book filled with information, and then evaporates, where does that information go? The laws of quantum mechanics insist information can never be truly destroyed. This is the black hole information paradox. The holographic principle emerged as a potential solution. It suggests the information about everything that falls into a black hole is not lost inside its mysterious singularity, but is instead smeared and encoded on the black hole's two-dimensional event horizon, the point of no return. Think of it like taking a three-dimensional sculpture and carefully flattening it into an intricate, two-dimensional painting. All the information needed to reconstruct the sculpture is preserved in the patterns of the paint. In this view, the three-dimensional space inside the black hole is a projection from the data on its two-dimensional boundary. The physicist Leonard Susskind and others then took a breathtaking leap. What if this is not just a property of black holes, but a fundamental feature of the entire universe? Our cosmos, with its three spatial dimensions, might itself be a holographic projection from a two-dimensional surface at the very edge of everything we can see. This idea found a precise mathematical home in a concept called the anti-de Sitter/conformal field theory correspondence, often shortened to add S/SUFD. It proposes a perfect duality, a complete dictionary, between a gravitational universe with three spatial dimensions and a quantum field theory that lives on its two-dimensional boundary. In simpler terms, the messy, complex physics of gravity and stars and galaxies in our 3D world has a perfect, equivalent description in the form of a flat, 2D quantum system without gravity at all. One is not more real than the other. They are two descriptions of the same reality. The mind-bending implication is that our perceived reality, the solidity of the ground beneath your feet, the vast depth of the night sky, the three-dimensional volume of your own body, is a projection. The true, fundamental reality, where the bits and bytes of existence are actually stored, exists on a distant, flat screen we can never see or touch. You are right now reading the subtitles of a cosmic movie while believing you are inside the film. This does not mean reality is fake, but that it is deeply relational, an emergent property of information. The universe is not made of tiny billiard balls, but of bits, and those bits live on a surface we perceive as the past. It suggests a profound limit to how much information any region of space can contain, defined not by its volume, but by its surface area. The cosmos is not just stranger than we imagine, it may be far flatter. If our reality is a holographic projection, a natural and terrifying question follows. Who or what is running the simulation? This is the simulation hypothesis, a modern philosophical argument that our universe is not a base reality, but an artificial construct, a digital universe running on the hardware of a civilization vastly more advanced than our own. The idea gained serious traction with philosopher Nick Bostrom's influential paper, which laid out a stark logical trilemma. He argued that at least one of three propositions is almost certainly true. First, that virtually all civilizations at our level of technological development go extinct before becoming capable of creating advanced simulations. Second, that any advanced civilization would have zero interest in running simulations of their own ancestors. Or third, that we are almost certainly living inside a computer simulation. The logic is statistical. If even a single advanced civilization survives and decides to run detailed simulations of its own history, and if computing power continues to grow, they could create astronomical numbers of simulated worlds, each populated with conscious beings who believe their reality is real. In such a scenario, the number of simulated minds would vastly outnumber the minds in the original base reality. Therefore, if you are a conscious being, the odds are overwhelmingly high that you exist inside one of those countless simulations, not in the original. This is not a claim that it is true, but a suggestion that we cannot dismiss it as mere science fiction. It is a probabilistic argument that forces us to confront the nature of our own existence. What would evidence for such a simulation look like? Proponents suggest we might find glitches in the matrix, subtle signs of optimization or shortcuts in the underlying code of physics. Just as a video game uses tricks like lowering detail for distant objects to save processing power, a simulated universe might have fundamental resolutions or limits. Some physicists have proposed looking for evidence of pixelation in the fabric of space-time itself, perhaps by studying the highest energy cosmic rays. If space is not perfectly smooth, but has a tiny, finite graininess, it could be a sign of the simulation's rendering limit. Others suggest the strange rules of quantum mechanics, where particles exist in fuzzy probabilities until observed, might resemble a universe that only renders details when necessary to conserve computational resources. The double-slit experiment, where a single particle seems to pass through two openings at once, could be seen as a lazy loading of possibilities, a way for the simulation to avoid calculating a definite path until a conscious observer forces it to commit. Even the speed of light, the universe's ultimate speed limit, could be interpreted as the processor clock speed of the cosmic computer, a limit on how fast information can be updated across the simulation. The hypothesis reframes our entire search for a theory of everything. We might not be discovering fundamental laws of nature, but reverse engineering the source code of a program we are trapped inside. This leads to unsettling, almost playful questions. If this is a simulation, who are the programmers? Are they our distant descendants, running ancestor simulations to understand their own past? Or are we the entertainment or experiment of an alien intelligence? The simulation argument does not provide comforting answers, but it radically expands the canvas of what might be possible, suggesting that the deepest mystery of the universe may not be its origin, but its authenticity. Authenticity implies a creator, but what if the cosmos requires no programmer at all? What if reality is not a simulation, but simply a consequence of pure abstract logic? This is the mathematical universe hypothesis, proposed by physicist Max Tegmark, and it represents perhaps the most extreme vision of a multiverse. In this view, our universe is not just described by mathematics, it is mathematics. More radically, every single mathematical structure that is logically consistent exists as a physical reality somewhere. This is Tegmark's Level 4 multiverse, the ultimate ensemble of all possible realities. Think of mathematics as a vast, infinite landscape. Somewhere in that landscape is the specific structure that corresponds to our universe, with its 3 spatial dimensions, 4 fundamental forces, and quantum mechanical rules. But that is just one point. Elsewhere in the mathematical realm are structures describing universes with 5 spatial dimensions, or with gravity 1,000 times stronger, or where the number pi has a different value. There are structures where time runs backward, where cause and effect are reversed, or where the very logic of existence operates under different rules, like a universe built not on classical logic, but on fuzzy or paradoxical systems. In this hypothesis, these are not just interesting equations on a chalkboard. They are all equally real physical universes. The mathematical structure is the physical reality. There is no distinction. This leads to a profound philosophical question that has haunted thinkers for millennia. Is mathematics something we humans invented, a useful tool to describe the world, like a language? Or is it something we discovered, a pre-existing eternal truth that exists independently of any mind? The mathematical universe hypothesis argues fiercely for the latter. In this view, mathematicians are not inventors. They are explorers, mapping out the contours of a timeless, abstract territory that was always there. The number pi, the Pythagorean theorem, the laws of calculus, they were not created when humans first wrote them down. They were eternal features of the mathematical landscape, waiting to be found. Our universe, then, is simply one of those features that has the property of containing self-aware substructures, which we call conscious beings. We are patterns of information that exist within a particular mathematical structure complex enough to perceive itself. This idea dissolves the boundary between the abstract and the concrete. The solidity of a rock, the warmth of sunlight, the feeling of love, all of these are just particular manifestations of an underlying mathematical pattern. It suggests that the ultimate nature of reality is not made of particles or fields, but of numbers, sets, and relationships. The implications are dizzying. It means that every story, every fantasy, every nightmare that can be described in a logically consistent mathematical framework is not just a fiction, but a reality playing out in some corner of the multiverse. A universe where dragons fly and magic works is real, provided you can write down its consistent governing equations. The hypothesis also offers a stark answer to the fine-tuning problem. Why are our physical constants so perfectly calibrated for life? Because in the infinite set of all mathematical structures, every possible set of constants exists somewhere. We find ourselves in the one that allows for our existence, not because it was designed, but because our consciousness is a feature that can only arise within such a structure. It is a cosmic version of the anthropic principle, but rooted not in physics, but in pure mathematics. This vision can feel cold and alien, reducing the rich tapestry of experience to mere equations. Yet, it is also strangely elegant, proposing a reality with no baggage, no unexplained initial conditions, no need for a creator or a simulator. Existence simply is because mathematics is. The universe is not just written in the language of mathematics. It is that language, speaking itself into being across an infinite library of possible forms. The mathematical universe suggests a reality built from eternal equations. But what if new universes are born from the most violent events within our own? This is the daughter universe theory, a breathtaking idea emerging from the frontier of quantum gravity, where the ultimate cosmic destroyers become creators. At the heart of this theory lies the black hole, a region of spacetime where gravity is so intense that nothing, not even light, can escape. For decades, the fate of anything that crossed a black hole's event horizon seemed grim and final, crushed into an infinitely dense point called a singularity, a place where our known laws of physics break down completely. But some physicists propose a different destiny, one where the singularity is not an end, but a new beginning. In this radical vision, the extreme conditions inside a black hole do not obliterate information and matter. Instead, they trigger a cosmic metamorphosis. The singularity could act as a bridge, a wormhole or a quantum tunnel, connecting our universe to a brand new region of spacetime that pinches off and becomes its own separate cosmos. This newborn universe, often called a daughter or baby universe, expands into its own existence, forever disconnected from its parent. Think of it like a cosmic seed pod. Our universe is the parent plant. A black hole forms representing the pod. Inside that pod, under immense pressure, a new seed, a new universe forms and is then ejected into its own independent reality. We, in the parent universe, only see the black pod, the event horizon, and have no way of seeing the new cosmos that has budded off within. The mechanism for this astonishing birth is tied to the quest to unite quantum mechanics with gravity. In the fiery chaos near the singularity, quantum fluctuations, tiny, random bursts of energy in the fabric of spacetime, could become so wildly amplified that they spark a new inflationary expansion, similar to the one that may have started our own cosmos. The black hole's immense energy and the scrambled information of everything it ever consumed become the raw material for this new Big Bang. This leads to a staggering possibility. Every black hole in our universe, from the small ones formed by collapsing stars to the supermassive monsters at the hearts of galaxies, could be a womb for a separate reality. Our entire cosmos might be teeming with unborn universes, each hidden behind an event horizon, and this process could be cyclical. Our own universe might itself be the daughter of a black hole that formed in a higher dimensional parent universe, part of an infinite, branching tree of cosmic ancestry. Perhaps the most intriguing aspect is the question of inheritance. Does a daughter universe get the same laws of physics as its parent? The answer is likely no, or at least not exactly. The violent physics of the singularity could scramble the fundamental constants, twisting them into new configurations as the new spacetime inflates and cools. The strength of forces, the masses of particles, even the number of spatial dimensions could be re-rolled in the cosmic lottery of that birthing moment. Our universe, with its life-friendly parameters, might be one fortunate outcome from a black hole in a cosmos with very different rules. This transforms our view of black holes from terrifying endpoints into cosmic engines of creativity. The information paradox, the question of what happens to the data of a fallen star, finds a poetic solution. The information is not lost, it is translated. It becomes the genetic code for a new reality, rewritten into the fundamental laws of a fledgling universe. In this grand vision, death and birth are woven together on the cosmic scale. A star's catastrophic collapse is not an ending, but a labor pain for a new cosmos. Every black hole is a closed door in our reality, but on the other side, it may be an open window onto an entirely new sky. Black holes may birth new realities, but what if the most perfect copy of our universe already exists, reflected in a cosmic mirror where everything is flipped? This is the theory of a mirror universe, a realm where fundamental symmetries of nature are reversed, creating a world that is eerily familiar, yet profoundly alien. The concept springs from a deep puzzle in particle physics involving a property called parity, which describes how the universe treats left and right. For a long time, physicists assumed the laws of nature were perfectly symmetrical, that they would work exactly the same if you viewed the universe in a mirror. A left-handed particle spinning one way would have a perfect mirror twin, a right-handed particle spinning the opposite way. But in the 1950s, experiments with radioactive decay shattered this assumption. They revealed that the weak nuclear force, which governs processes like radioactive decay, has a profound handedness, a built-in preference for left over right. In our universe, certain particles only interact via the weak force if they are spinning in a left-handed way. This means the universe is not perfectly symmetrical. It has a subtle bias, a cosmic chirality. This discovery led to a fascinating question. Could there be a parallel universe where this bias is exactly flipped? A mirror cosmos where the weak force prefers right-handed particles, where the very concept of left and right is reversed relative to our own. In such a universe, the building blocks of matter would be mirror images of our own. A mirror proton would spin the opposite way. A mirror DNA helix would twist in the opposite direction. If you could somehow step into this realm, you would find a world that seems recognizable, but where the very handedness of life's fundamental molecules might be inverted. This idea moves from speculation toward testable physics with a ghostly particle called the neutrino. Neutrinos are nearly massless, chargeless particles that barely interact with matter, passing through the entire Earth as if it were empty space. They come in 3 known types or flavors. Intriguingly, neutrinos have been observed to oscillate, spontaneously changing from one flavor to another as they travel. This oscillation implies they have a tiny mass, a fact not predicted by the original standard model of particle physics. Some theorists propose this strange behavior could be a window into the mirror world. They suggest there might be a 4th type of neutrino, a sterile neutrino, that does not interact via any of the known forces except gravity. This sterile neutrino could be constantly oscillating with our ordinary neutrinos. Where does the extra flavor go? One compelling possibility is that it oscillates into a mirror neutrino, a particle that belongs entirely to the hidden mirror sector. In this model, our neutrinos are briefly dipping into the mirror universe and back, explaining their mysterious transformations. This mirror realm would be built from its own set of particles and forces, a complete shadow copy of our standard model, but with the parity violation reversed. The 2 universes would be woven together only by the faintest of threads, gravity, and perhaps these neutrino oscillations. They would occupy the same space as us, but their particles would be invisible to our detectors, their light unseen by our telescopes. We would never see a mirror star or a mirror galaxy directly, because the photons they emit would be mirror photons, which do not interact with our eyes or our instruments. The only way we might sense their presence is through gravitational effects, or by carefully measuring the precise ways our own neutrinos behave, hunting for anomalies that betray a secret conversation with another reality. The mirror universe theory resonates deeply with science fiction, from the antagonistic mirror universe of Star Trek to the unsettling parallel worlds of fantasy. Yet its foundations are in serious attempts to restore a beautiful symmetry to the laws of physics and to explain the lingering mysteries of the neutrino. It proposes that the asymmetry we observe, our left-handed universe, is only half of a grander, perfectly balanced design. Somewhere in a realm of inverted parity, the other half exists in perfect counterbalance, a hidden reflection waiting to be glimpsed in the faintest wobble of the most elusive particle we know. A mirror universe shares our space unseen, but another theory proposes we are not sharing space at all. We are trapped inside it, prisoners of the ultimate cosmic gravity well. This is the startling hypothesis that our entire universe exists inside a black hole. To make sense of this, we must reframe the most famous event in cosmology, the Big Bang. In our standard view, the Big Bang was an explosion from a point of infinite density, a singularity that created space and time. Now, consider the interior of a black hole from the perspective of something falling in. As you cross the event horizon, space and time swap roles. The radial direction toward the singularity becomes not a place in space, but a moment in future time. You are not falling to a location. You are falling toward a future moment where you will inevitably hit the crushing singularity. In this view, the singularity is not a point in space, but the end of time for anything inside the black hole. Now, run the film in reverse. What if our Big Bang was not the beginning of time, but the end of time for something else? What if our expanding universe is simply the interior of a colossal black hole, viewed from the inside, with the singularity in our distant past? In this model, the hot, dense state of the early universe is exactly what you would expect to see if you were looking back toward the moment of formation, the singularity from which our cosmos was born. The expansion we observe is not an explosion into nothing, but the continued stretching of spacetime within the black hole's interior. This idea gains traction when we examine the numbers. The density of the universe at the moment of the Big Bang can be calculated. So can the density required to form a black hole of a given size. Remarkably, if you calculate the density needed to turn our entire observable universe into a black hole, the resulting Schwarzschild radius, the size of its event horizon, is roughly the same as the estimated size of the universe at that early moment. It is a tantalizing numerical coincidence that suggests our cosmos may have the precise properties of a black hole's interior. This leads to a profound nesting doll vision of reality. Our universe exists inside a black hole, which itself exists within a larger parent universe. That parent universe may also reside within a black hole in a grandparent universe, creating an infinite regression of cosmic containment. Each universe is a separate bubble of spacetime, born from a singularity and forever hidden behind an event horizon from the outside world. But how did we get here? The birth canal for our universe might be something even stranger than a black hole, a theoretical opposite known as a white hole. While a black hole is a region from which nothing can escape, a white hole is a region from which nothing can enter. It is a point of pure, relentless expulsion, spewing out matter and energy but allowing nothing in. If a black hole's singularity represents the end of time, A white hole singularity could represent the beginning. Some models suggest that when a black hole forms in the parent universe, it connects via an Einstein-Rosen bridge, or wormhole, to a white hole in a newborn daughter universe. The violent physics at the bridge's neck could trigger inflation, creating the hot Big Bang conditions we see as our origin. From the perspective of the parent universe, it's a black hole consuming matter. From our perspective inside, it's a white hole giving birth to everything we know. This could even explain one of the greatest mysteries in modern cosmology, dark energy. The observed acceleration of the universe's expansion might not be driven by a mysterious energy field. Instead, it could be a gravitational effect caused by our position within this colossal structure. As we, inside the black hole, move further from the central singularity of our past, the geometry of the interior could naturally produce an accelerating expansion, mimicking the effects of dark energy. We are not being pushed apart by a force, but rather, the space within our cosmic prison is stretching in a specific, predetermined way. The implications are haunting. We look out at the night sky, at galaxies rushing away from us, and believe we are seeing the grandeur of an open, infinite cosmos. But we may instead be staring at the walls of our cell, the interior surface of an event horizon so vast it appears as a universe. Our entire history, from the first star to this very moment, is the story of the interior of a black hole, a story written in escaping light that can never reach the outside, forever trapped within the ultimate gravitational well. A black hole's interior may be our entire reality, but what if time itself is circular, and our universe is just one link in an endless chain of cosmic rebirth? This is the conformal cyclic cosmology, a breathtakingly elegant theory proposed by the Nobel laureate Sir Roger Penrose. It offers a vision of eternity not through parallel branches or hidden dimensions, but through the transformation of the universe's own scale and information. Penrose's theory begins by confronting the two most extreme epochs of cosmic history, the hot, dense Big Bang and the cold, empty heat death. In the standard model, these are opposites, a beginning and an end. But Penrose saw a profound symmetry. In the far, far future, trillions upon trillions of years from now, the universe will have expanded so much that all matter will have decayed, all black holes will have evaporated via Hawking radiation, and only an endless sea of massless particles, like photons and gravitons, will remain. In this state, the universe loses all sense of scale. There is no ruler to measure distance, no clock to tick off time, because all structures that could provide a reference have dissolved. The cosmos becomes smooth, featureless, and timeless. This is the key. Penrose realized that this distant future state, what he calls the remote future, is mathematically identical in its structure to the initial state of the Big Bang, the remote past. Both are states of infinite smoothness, where the concept of size becomes meaningless. In the language of geometry, they are connected by a process called conformal rescaling, which can stretch or shrink the entire universe without changing its shape. Think of it like a map. You can have a map of a city on a single page, or you can blow that same map up to cover a football field. The distances and scales are completely different, but the relationships, the shapes of the streets and parks, are preserved. In conformal cyclic cosmology, the entire history of our universe, from the Big Bang to heat death, is one such map. When it reaches its maximally stretched, smooth end state, it can be conformally rescaled, shrunk down mathematically to become the hot, smooth starting point for a new universe, a new aeon. The end of our time becomes the beginning of another's. Our universe is not a line with a start and finish, but a circle, connected seamlessly to the next circle in an infinite, unbroken chain. This leads to one of the theory's most startling predictions: the existence of Hawking points in the cosmic microwave background. According to Penrose, not all information from our aeon is lost when it resets. The most titanic events, the evaporation of supermassive black holes over unimaginable timescales, could leave faint imprints. As these monstrous black holes finally evaporate in the remote future of our aeon, they release enormous amounts of energy in the form of Hawking radiation. This burst of energy, Penrose suggests, could be conformally mapped into the next aeon as a circular pattern of slightly raised temperature in the cosmic microwave background, the afterglow of its Big Bang. These would be faint, concentric rings or points on the sky, whispers of dead black holes from a universe that existed before our own. Some analyses of cosmic microwave background data have claimed to detect exactly such anomalous, circular patterns, though the findings remain highly controversial within the cosmology community. If confirmed, they would be the first direct evidence of a pre-Big Bang universe, a fossil from a previous cosmic cycle. Visualizing this is to see time not as a river flowing in one direction, but as a series of endless, connected circles. Each aeon begins with a hot, dense bang, expands and structures itself into galaxies and life, then gradually unravels over eons into a featureless void, only to be reborn again from that very void's transformation. In this view, the heat death is not a tragic finale of stillness, but a necessary purification, a reset that allows the universe to begin again, fresh and smooth, ready to write a new story with the same fundamental laws, but potentially entirely new arrangements of matter and life. The chain of aeons is eternal, with no first cause and no ultimate end. A cosmic Ouroboros, the snake eating its own tail across the expanse of eternity. Penrose's eternal circles suggest a cosmos of endless rebirth, but another theory proposes a static, frozen landscape of every possible universe, waiting to be discovered. This is the landscape multiverse, the ultimate hidden portfolio of realities, and it emerges from the deepest mathematical trenches of string theory. We've touched on string theory's extra dimensions and branes, but its most profound implication is a staggering number of possible solutions. The equations of string theory do not yield a single, unique set of laws for our universe. Instead, they describe a colossal array of possibilities, perhaps 10 to the power of 500 distinct configurations. Each configuration represents a different way for the extra dimensions to be curled up and stabilized, and each yields a different set of physical constants, a different vacuum state for reality. This collection is the landscape, a vast, abstract terrain where every valley, hill, and plateau corresponds to a potential universe with its own unique physics. Our cosmos is just one point in this unimaginably vast cosmic catalog. The existence of this landscape offers a powerful, if controversial, answer to the fine-tuning problem. Why is our universe so perfectly calibrated for complexity in life? Why is gravity just strong enough to form stars, but weak enough to allow planets? Why are the nuclear forces balanced to create stable atoms? In the landscape view, there is no deeper reason. Every possible set of constants exists somewhere in the portfolio. We, as conscious observers, can only find ourselves in one of the rare universes where the numbers allow for our existence. This is the anthropic principle applied on a cosmic scale. We do not observe a life-friendly universe because it was designed, but because our very observation requires a universe capable of producing observers. It is a cosmic version of the observation that a fish lives in water not because the ocean was made for fish, but because fish evolved within the ocean's specific conditions. The landscape turns the search for a unique theory of everything on its head. Instead of one elegant equation describing our world, we may have a near-infinite menu, and we simply inhabit one of the few entries that leads to us. This idea is not without its fierce critics. The primary charge is that it makes string theory seemingly untestable and unscientific. If every possible outcome exists somewhere, how can we ever make a prediction that could be proven wrong? How do we distinguish a theory that explains everything from one that explains nothing? Proponents argue that while we cannot visit another valley in the landscape, we can look for signatures within our own universe that point to this broader structure. The specific pattern of cosmic inflation we observe, the nature of dark energy, even the detailed properties of the Higgs boson, could all be clues that our vacuum state is one among many, and that our physics is not fundamental but local. The landscape multiverse is a humbling proposition. It suggests that the laws we hold as immutable truths are more like local bylaws, relevant only in our cosmic neighborhood. Somewhere in the landscape, a universe exists where gravity repels, where time has two arrows, or where light moves at a crawl. It is a hidden archive of every physical possibility, a silent, static library where our story is just one book on an endless shelf. Its pages open simply because we are here to read them. The landscape multiverse offers a near-infinite portfolio of possible worlds. But this sheer abundance of possibilities births one of the most unsettling paradoxes in all of cosmology. Known as the Boltzmann brane, this thought experiment suggests that in a truly eternal and random cosmos, the most likely observer might not be you, with your memories and a universe of history, but a lone, self-aware brain that has just popped into existence from pure chaos. The paradox is named for Ludwig Boltzmann, the 19th century physicist who helped develop statistical mechanics. He grappled with a similar problem, explaining why we see order around us when the second law of thermodynamics states the universe tends toward disorder or entropy. His solution was that we live in a rare, low-entropy fluctuation within a much larger, high-entropy cosmos. In an eternal universe, even the most improbable events will eventually happen by random chance. A room full of gas molecules, all bouncing around randomly, could by sheer accident suddenly all gather in one corner. It is astronomically unlikely, but given enough time, it will occur. Apply this logic to the entire cosmos, especially within frameworks like eternal inflation or an infinite multiverse. Over infinite time and across infinite space, every possible configuration of particles will spontaneously arise from quantum fluctuations. This includes the configuration of a fully formed, self-aware human brain, complete with false memories of a past, a sense of a present, and the illusion of an external universe. According to the brutal math of probability, it is vastly more likely for a single, disembodied brain to fluctuate into existence than for an entire 13.8 billion year-old ordered universe with galaxies, planets, and billions of conscious beings to form. Think of it like shaking a box of Scrabble tiles. It is far easier to randomly shake the tiles to spell a single, short word-like brain than to shake them into the complete, ordered text of an entire encyclopedia. If our cosmos is eternal and random, then the number of these solitary, hallucinating Boltzmann brains should overwhelmingly outnumber the number of ordinary observers like us, who evolved within a long, structured cosmic history. Therefore, if you are a conscious being, the odds suggest you are probably a Boltzmann brain, experiencing a momentary delusion of reality rather than a product of a vast, ancient universe. This is the paradox. Our cosmological theories that posit an eternal, inflationary multiverse seem to predict that we should not exist as we believe we do. The observation of a coherent, low-entropy past and a seemingly lawful universe becomes a monumental anomaly. Scientists take this paradox seriously because it acts as a razor, testing the logical limits of our cosmic models. If a theory predicts that Boltzmann branes are the most common observers, then that theory has a fatal flaw, as it contradicts the basic data point of our own ordered existence. Resolving the paradox forces physicists to seek models where ordinary observers like us are more probable, or where the conditions for Boltzmann branes are impossible. Some propose our universe is not eternal in the past, that it had a definite beginning which set a low entropy boundary, making our ordered history not a random fluctuation, but a mandated starting condition. Others suggest that in an inflating multiverse, while branes could form, they would be instantly diluted and destroyed by the relentless expansion before they could have a coherent thought, while stable universes like ours persist. The Boltzmann brane is more than a clever puzzle. It is a profound meditation on the nature of observation and reality. It asks how we can trust any memory or any law of physics if, in principle, they could be a fleeting fiction manufactured by random chance. The fact that we do trust them, that we see a universe of deep structure and consistent history, may be the strongest clue we have that our cosmos is not a random accident in an eternal sea of chaos, but a system with a genuine beginning and a fundamental direction to time. Our very sanity, it seems, is a cosmological datum. The Boltzmann brane paradox forces us to question the very fabric of our memories, but it hinges on a cosmos already in existence. What if we push further back, to the ultimate question of why there is something rather than nothing at all? This leads to a theory so profound it seems to skirt the edge of magic, the idea that our entire universe could have sprung from a quantum fluctuation in a state of absolute nothingness. At the heart of this idea is a cornerstone of quantum mechanics, the principle that empty space is not truly empty. Even in a perfect vacuum at the tiniest scales, there is a seething, restless energy. Virtual particle pairs, matter and antimatter, constantly wink into and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other and paying the energy back. This is the quantum foam, a realm of unstable potential where the rules of classical physics break down. The physicist Lawrence Krauss, among others, has taken this concept to its cosmic limit. He proposes that if a quantum fluctuation can create a pair of particles from nothing, then, given the right conditions and enough time, a fluctuation could create an entire universe. In this view, the nothing before our Big Bang was not an empty void in the classical sense. It was a state of unstable potential governed by the laws of quantum physics, a realm without space or time as we know them, but brimming with probabilistic activity. From this quantum foam of potential, a fluctuation of sufficient magnitude could have tunneled into existence, triggering an inflationary expansion that became our cosmos. Our universe, in this scenario, is the ultimate free lunch, emerging from a natural, if extraordinarily rare, quantum event. This immediately sparks a fierce philosophical debate. What do we mean by nothing? Krauss defines it as a state devoid of particles, forces, and even dimensions, but still subject to the laws of quantum mechanics. Critics argue that quantum fields and laws themselves are something, a pre-existing framework. They contend that true philosophical nothing would lack even the potential for something to arise. This debate highlights the chasm between the physicist's operational definition and the philosopher's abstract one. Yet, the power of the quantum fluctuation idea is how seamlessly it integrates into a grander multiverse picture. If one universe can pop into existence from such a fluctuation, why not many? Imagine the primordial quantum foam not as a static blank slate, but as an eternal, bubbling cauldron of potential. Universes with different laws and constants could be constantly nucleating, inflating into their own realities, and perhaps even decaying back into the foam. Our cosmos would be just one bubble in an endless, frothing sea of spontaneous creation, where the concepts of a single beginning or a final end lose all meaning. In this eternal multiverse, most universes might be stillborn, collapsing instantly or expanding into barren emptiness. Only a rare few, by sheer statistical chance, would have the precise conditions for stars, planets, and life. Once again, we find ourselves in a fortunate cosmos, not because it was designed, but because we could not exist in any of the countless others. This vision is both humbling and liberating. It suggests that existence may not require a first cause or a creator, but could be a natural, inevitable product of the fundamental rules of reality, however those rules themselves came to be. The universe from nothing is not a story of creation ex nihilo in the traditional sense, but one of spontaneous generation from the fertile ground of quantum possibility, where nothing is, paradoxically, the most pregnant state of all. Quantum fluctuations may birth universes from apparent nothingness, but they leave a fundamental question untouched. What is the true nature of time itself? We have been speaking of beginnings and endings, of past and future, as if time were a one-way street. Yet a radical reinterpretation of quantum mechanics suggests this is an illusion. Time may be perfectly symmetric, and our universe could possess not just a definite past, but a definite future as well. This is the two-state vector formalism and its more intuitive cousin, the transactional interpretation proposed by physicist John Cramer. It begins with the enduring mystery of the double-slit experiment. In the standard view, a single particle like an electron travels as a probability wave, passes through both slits simultaneously, interferes with itself, and only collapses into a definite location when it is measured at the screen. This seems to demand a bizarre, instantaneous action. The transactional interpretation offers a beautifully symmetrical alternative. It proposes that when an electron is emitted from a source, it sends out an ordinary wave forward in time, an offer wave. When that wave reaches a possible destination, like a specific point on the detector screen, that destination sends a confirmation wave backward in time. A transaction is only completed, and the particle only appears at a definite location, when these forward and backward waves meet in a kind of handshake across time. The particle's entire history, from emission to detection, is determined by this two-way negotiation between past and future. In this view, the famous wave function collapse is not a sudden event in the present, but the completion of a loop that was always destined to happen. The future is not open. It is just as fixed and real as the past, and it reaches back to guide events into being. This paints a startling picture of reality. Every quantum event, from the decay of an atom to the firing of a neuron in your brain, is the result of a transaction spanning the entire timeline of the universe. It suggests that time, at its most fundamental level, is not a flowing river but a static block, where all moments coexist. This leads to a breathtaking cosmological possibility. If time is symmetric, then the two ultimate boundaries of our universe, the Big Bang and the final Big Crunch or heat death, might not be a beginning and an end. They could be the two fixed ends of a single, timeless structure. Imagine the entire history of our cosmos as a four-dimensional loaf of bread. One crust is the hot, dense singularity of the Big Bang. The other crust is the cold, expanded, featureless state of the far future. We, living inside the loaf, experience a slice at a time, perceiving a relentless march from one crust to the other. But from a God's eye view outside of time, the entire loaf exists at once, complete and unchanging. In some elaborations of this idea, the two ends could even be reflections of each other. The Big Bang and the Big Crunch might be connected, forming a closed time-like curve. From our perspective, we are expanding away from the bang and toward the crunch. But from the perspective of the crunch itself, looking backward, its own contraction could be seen as an expansion from its point of view, a mirror image universe where time runs in the opposite direction. In this symmetrical cosmos, there could be a hidden twin to our reality, a universe of reverse entropy unfolding from our future toward our past, its inhabitants believing they are expanding from their own Big Bang, which is our distant future. We would be forever separated by the thermodynamic arrow of time, each universe's consciousness perceiving an opposite flow from order to disorder. This is not time travel, but a profound duality woven into the fabric of existence. The implications for free will and destiny are profound. If the future is already out there, sending confirmation waves backward to sculpt the present, does choice have any meaning? Or is our sense of decision-making simply the local experience of a transaction that was always going to happen? The theory does not make the universe feel predetermined so much as whole, a single, breathtaking sculpture viewed from within. We are not passengers on a river of time, but explorers inside a timeless crystal, mistaking its facets for a sequence, unaware that the light within has already traveled from the far side and back. The symmetric block of time presents a universe that is whole and complete, yet our direct experience feels nothing like that. We perceive a single, definite reality unfolding moment by moment, not a superposition of all possibilities. The mechanism that bridges these two descriptions, that transforms the quantum world's fuzzy potential into our concrete classical experience, is called decoherence. And it may be the very process that actively hides the multiverse from our view. Quantum decoherence is not a mysterious collapse, but a natural consequence of interaction. In its pristine state, a quantum system like an electron can exist in a superposition, being in multiple states at once. But the moment it interacts with its environment, even with a single stray photon, something profound happens. Information about the system's state leaks out into the environment, becoming entangled with countless other particles. This entanglement spreads the quantum coherence, the delicate interference pattern, so thinly across the universe that it becomes practically impossible to recover. From the perspective of any local observer, the superposition appears to vanish, and the system settles into what looks like a single, classical state. In the many worlds interpretation, decoherence is the engine that drives the branching. It does not destroy the other possibilities. It simply severs their connection to our branch of reality. Think of it like a detective losing a suspect's trail in a crowded city. The suspect did not vanish into thin air. They simply merged with the throng of people, making it impossible for the detective to track them. The information about where they went still exists, but it is now hopelessly scrambled across the entire population. Similarly, when you measure an electron's spin, The outcome you see becomes entangled with the particles in your measuring device, your eyes, and your brain. The version of you that sees spin up is now entangled with one outcome, while the version that sees spin down is entangled with the other. Decoherence ensures these two versions can no longer interfere with each other. They become causally disconnected, each following its own independent timeline. This is the hiding multiverse. Every quantum event where decoherence occurs is not a moment of selection, but of division and concealment. The other branches of the wave function do not cease to exist. They simply recede from our awareness, becoming hidden universes, forever separate and inaccessible because the information that would connect us to them is irretrievably dispersed into the environmental noise. The universe is not choosing one reality. It is constantly dividing into countless realities and then hiding most of them from each other. The scale of this concealment is staggering. It happens not just in laboratory experiments, but everywhere all the time. The sunlight hitting a leaf, the wind rustling a page, the electrical signals in your nervous system. All of these are processes involving trillions of quantum interactions, each one a potential branching point where decoherence hides alternative outcomes. The solid, definite world you perceive is not the whole story. It is just the single branch you are entangled with, while a vast, invisible tree of other possibilities grows silently alongside it, forever out of reach. This view transforms the nature of probability. When we say an electron has a 50% chance of spinning up, we are not describing ignorance about a predetermined outcome. We are describing the objective weight of the branch we will end up on. You are not rolling dice to see what happens. You are stepping onto a path that splits, and your continued existence follows one fork, while another, equally real version of you follows the other. The hiding is so perfect, the disconnect so absolute, that we never feel the split or sense the loss. We only ever experience the one, consistent thread of reality that our consciousness is entangled with, a single storyline carefully isolated from the infinite library of other tales. Decoherence hides the branching quantum world, but another vision of reality argues we are missing a fundamental force shaping the cosmos itself. The plasma universe theory, sometimes called the electric cosmos, challenges the gravitational orthodoxy of modern astrophysics, proposing that electricity and magnetism are the primary architects of the universe. In this alternative model, the vacuum of space is not empty, but filled with a diffuse, electrically conductive plasma, a sea of charged particles. Across this cosmic ocean flow vast, invisible currents, weaving galaxies and stars together into a single, interconnected circuit of unimaginable scale. Here, gravity is not the sole master of cosmic structure. Instead, it is the long-range force of electromagnetism, operating through twisting filaments of plasma known as Birkeland currents, that sculpts spiral galaxies, powers stars, and even shapes the surfaces of planets. Proponents of this model, like the late physicist Hans Elfvén, a Nobel laureate for his work on magnetohydrodynamics, suggest we live in an electric universe, one part of a larger galactic circuit whose ultimate power source remains a mystery. They point to the filamentary structures seen throughout the cosmos, from the intricate webs of nebulae to the vast tendrils connecting galaxy clusters, and argue these are not merely gravitational artifacts, but the visible signatures of billion light-year-long electric currents flowing through space. In this view, a star is not simply a ball of gas igniting under gravity's crush, but a focused glow discharge, an electric arc in a galactic circuit. Its energy comes not solely from internal nuclear fusion, but from external electrical currents flowing into it from the surrounding plasma. This could explain puzzling stellar behaviors, like the intensely hot solar corona, which is millions of degrees hotter than the Sun's surface, a fact that standard models struggle with. The theory extends to planetary geology, suggesting that features like canyons and craters might not always be the result of impacts or water erosion, but of colossal electric arcs scarring a planet's surface in the distant past, in events called cosmic thunderbolts. This is where the plasma universe model diverges most sharply from mainstream cosmology and draws its strongest criticism. It proposes a hidden electromagnetic history for many cosmic phenomena, one that often relegates the Big Bang and black holes to secondary importance or rejects them entirely. Mainstream astrophysics, while fully acknowledging the role of plasma and magnetic fields in space, places them within the well-tested framework of gravitational dominance and the standard cosmological model. The vast majority of scientists argue that the large-scale structure of the universe is definitively shaped by gravity and dark matter, not by large-scale electric fields, which would quickly short out in the conductive plasma of space. They see the electric universe as a collection of interesting analogies that fails to make the precise, quantitative predictions that define a robust scientific theory. Yet, for its proponents, this rejection is a sign of a paradigm unwilling to question its foundations. They argue that by ignoring the potential for large-scale electrical forces, we are missing a fundamental key to understanding everything from the formation of galaxies to the historical myths of ancient civilizations, which they sometimes interpret as eyewitness accounts of plasma discharges in the sky. The debate is less about the existence of plasma, which is undeniable, and more about its ultimate cosmic significance. Are we living in a universe of isolated islands of matter bound by gravity? Or are we nodes in a shimmering electric web, alive with currents that light the stars and connect all things? The plasma universe insists the hidden truth is written not in the silent pull of mass, but in the dynamic flow of charge across the void. The electric cosmos challenges our foundational assumptions, but decades before it, a far more established theory dared to question the very idea of a beginning. This was the steady-state theory, the elegant and formidable rival to the Big Bang for much of the 20th century. Its core proposition was beautifully simple. The universe has always existed and will always exist, looking roughly the same at any point in time. There is no creation, no explosive origin, no ultimate fate. To maintain this eternal, unchanging density in the face of observed expansion, its proponents, including Fred Hoyle, Herman Bondi, and Thomas Gold, proposed a radical mechanism, the continuous creation of matter. Out of the void, at an imperceptibly slow rate, new hydrogen atoms would simply appear, just enough to fill the gaps as galaxies drifted apart, ensuring the cosmic density remained constant forever. For a time, this vision of an eternal, self-renewing cosmos held immense appeal, offering a philosophical alternative to the theological implications of a singular beginning. But evidence began to turn against it. The discovery of the cosmic microwave background radiation in 1965 was a decisive blow. This faint, uniform glow filling the sky was the predicted afterglow of a hot, dense early universe, a smoking gun for the Big Bang. The steady-state theory, in its classic form, could not explain it, and it faded from the mainstream. Yet, like a phoenix, the spirit of the steady state has never fully died. In modern cosmology, it has found new life through fascinating revisions that merge its eternal nature with our observed history. One compelling idea places our Big Bang universe inside a much larger, eternal meta-universe that is in a steady state. In this view, our entire cosmos, with its explosive beginning and eventual fate, is just a local fluctuation within an infinite, timeless whole. Imagine a calm, endless ocean. Our universe is a single, temporary whirlpool within it. From our perspective inside the whirlpool, we see a dramatic beginning, rapid currents, and a structure that will eventually dissipate. But from the perspective of the ocean itself, nothing has truly begun or ended. The overall density and state remain constant. The Big Bang was not the start of everything, but the start of our local region. Furthermore, concepts from inflationary cosmology can be woven into this framework. Eternal inflation, with its endless froth of bubble universes, creates a meta-universe that, on the largest scales and over infinite time, achieves a kind of steady state. Individual bubbles like ours are born and evolve, but the overall landscape remains statistically unchanged, an eternal, dynamic equilibrium of creation and decay. In such a multiverse, the question, what happened before the Big Bang, receives a profound answer. There was no before for the whole of reality, only a different arrangement of the eternal meta-cosmos. Our local history is real, but it is not the whole story. The revised steady-state idea challenges us to separate what is truly universal from what is merely local. The laws we discover, the history we trace, may be the bylaws and annals of our cosmic province, not the constitution of existence itself. It suggests that the deepest truth of the cosmos might not be a story with a beginning, middle, and end, but an endless, breathing tapestry, where our fiery genesis is but one thread in an immortal weave. The universe may not be a machine, but a mind. One of the most radical and speculative ideas emerging from the intersection of physics and computer science is that the cosmos itself is a vast neural network, a learning, evolving computational system. In this view, the fundamental building blocks of reality, particles like electrons and quarks, are not the primary substance of the universe. Instead, they are emergent phenomena, patterns of activity that arise from the deeper, ceaseless computation of a cosmic-scale neural network. Think of the way a complex image emerges on your computer screen from the interactions of millions of tiny pixels. The pixels are not the image. They are the medium through which the image is expressed. Similarly, particles might be the pixels on the screen of a universe-wide processor, momentary patterns in a deeper flow of information. This idea suggests that the laws of physics as we know them are not fundamental, immutable rules carved in the fabric of space-time. They could be learned behaviors, regularities that have emerged over cosmic time as this vast network optimized itself, settling into stable patterns through a process akin to machine learning. The evolution of the universe, from a hot, simple plasma to a cold, complex web of galaxies and life, might not be a random unfolding governed by fixed equations. It could be the universe learning about itself, a cosmic process of self-organization where complexity is not an accident, but an inevitable outcome of a system built to evolve and compute. This leads to a staggering implication about the nature of other universes. If our cosmos is one particular neural network that has settled into a stable configuration, then other universes in a multiverse could be entirely different networks, running different algorithms with different emergent laws. One universe might be a simple, repetitive pattern, a cosmic echo with no variation. Another might be a chaotic, ever-changing storm of computation where nothing stable ever forms. Our universe, with its delicate balance of order and chaos, its capacity for structure and consciousness, could represent a particularly successful and complex algorithm in a cosmic library of possible programs. The theory reframes the deepest questions. The mystery of why our laws seem so finely tuned for complexity is not about a designer or a statistical fluke in an infinite landscape. It becomes a question of which computational architectures can support long-term, stable computation that leads to rich, emergent phenomena. We exist in a universe that is, in a very real sense, capable of understanding itself, because its underlying structure is that of a learning system. This vision blurs the line between the physical and the informational, between existence and computation. It proposes that the universe is not just described by mathematics, but is engaged in a perpetual act of calculation, and we are both its products and its participants, nodes of awareness within a cosmic brain that is slowly waking up to its own nature. The universe as a cosmic mind suggests a reality built from information. But what if the very fabric of space and time is not smooth and continuous, but granular, like the pixels on a screen? Causal set theory proposes exactly that, and from its discrete foundation emerges a new vision of hidden universes. In this radical approach, spacetime itself is not the smooth, flowing canvas of Einstein's relativity. Instead, it is composed of fundamental, indivisible units, the atoms of spacetime. Think of the universe not as a continuous sheet of fabric, but as a vast, shimmering chainmail, where each tiny link is a fundamental event, a point in the causal set. The only property these atoms possess is their relationship to one another, a simple before or after. One event either precedes another, follows it, or is completely unrelated. This web of causal relationships, this tapestry of before and after, is what generates our entire experience of a four-dimensional universe with space and time. The smooth geometry we perceive, the curvature that guides planets and light, emerges from the collective pattern of these discrete links, much like the smooth curve of a mosaic emerges from thousands of tiny, jagged tiles when viewed from a distance. This discrete nature leads to a profound implication for a multiverse. If our universe is one specific causal set, one particular arrangement of these spacetime atoms with a specific history of cause and effect, then other arrangements are not just possible, they are inevitable in a grander scheme. Imagine an endless cosmic workshop where spacetime atoms exist as raw material. Different sets of these atoms can be linked together in entirely different patterns, creating separate causal sets that are completely disconnected from one another. Each set would have its own internal network of cause and effect, its own unique history of which events led to which others. These would be independent universes, each with its own emergent geometry, its own arrow of time, and its own laws of physics flowing from the particular pattern of its causal links. Because the sets are disconnected, an event in one universe has no causal link whatsoever to an event in another. They are hidden in the most absolute sense, not separated by vast distances or higher dimensions, but by a fundamental lack of any connection that could allow information, light, or influence to pass between them. One universe might have a causal set that produces the four dimensions we know. Another might generate a cosmos with 7 spatial dimensions. One set could link its atoms in a way that creates a cyclical time, where the causal chain loops back on itself. Another might produce a universe where time is branching, or where cause and effect are only partially ordered, leading to a reality of profound statistical fluctuation. In the causal set multiverse, the diversity is not in the substance, for all are made of the same kind of spacetime atoms, but in the architecture of their connections. Our experience of a universe that began with a big bang and unfolds in a linear, expanding fashion is simply the story written by one particular, immensely complex causal pattern. Other patterns write entirely different stories, cosmic narratives we can never witness because to do so would require a causal link that, by definition, does not exist. This vision presents a cosmos built not from substances or forces, but from pure relational structure, where existence itself is defined by what leads to what, and where every possible story of cause and effect is being told somewhere in the silent, disconnected library of all possible causal sets. Supersymmetry whispers of a universe that is far more balanced and elegant than the one we perceive. It is a profound mathematical symmetry that many physicists believe must be woven into the fabric of reality, proposing that for every known particle in the Standard Model, there exists a hidden superpartner. For every quark, there is a squark. For every electron, a selectron. For every photon, a photino. These superpartners are not merely duplicates. They possess a different quantum spin, a fundamental property that shifts them into the shadow realm of the hidden sector. In a perfectly supersymmetric universe, these partners would be identical in mass and force to their twins, and the cosmos would sing with a harmony we do not observe. The fact that we do not see a selectron sitting next to an electron tells us this symmetry is broken in our current cold universe. But in the unimaginable heat and energy of the cosmos's first moments, physicists believe supersymmetry would have been restored. In that primordial forge, every particle and its superpartner would have been indistinguishable, dancing together in a state of perfect balance, a hidden symmetry that may have been crucial for the universe to stabilize and expand as it did. As the cosmos cooled, this symmetry broke, and the superpartners acquired enormous masses, becoming too heavy to be produced in any particle collider or cosmic event we commonly witness today. They retreated into a hidden sector, a parallel particle world that coexists with our own, but interacts with it only through the faintest of threads, gravity and perhaps the weak nuclear force. This is where the theory connects to one of the greatest mysteries in cosmology, dark matter. The lightest of these superpartners, often called the neutralino, is a prime candidate. It would be stable, massive, and barely interacting, precisely the profile required for the invisible gravitational glue that holds galaxies together. In this view, dark matter is not some exotic, unknown substance, but the ghostly remnant of a broken cosmic symmetry, a hidden population of superpartners that form a vast, parallel universe interwoven with our own, felt only by its gentle gravitational pull on the stars. We are surrounded by an invisible architecture built from the other half of reality, a silent partner in the cosmic dance that began at the dawn of time. Supersymmetry suggests a hidden partner for every particle, but what if the entire universe has a hidden twin, not in composition, but in form? There is an old, almost poetic idea that the atom is a miniature solar system, with electrons orbiting a nucleus-like planets around a sun. This visual analogy is compelling, but it is fundamentally wrong. Quantum mechanics revealed that electrons do not travel in neat orbits. They exist in fuzzy clouds of probability, governed by rules utterly alien to the gravity-driven dance of planets. The solar system model, while a useful stepping stone, was ultimately a beautiful misconception. Yet, the intuition behind it points to a deeper, more haunting question about the architecture of reality. Could there be a genuine symmetry of scale, a cosmic echo where patterns repeat not by accident, but by design? This is the theory of a fractal or nested cosmos, where the universe we inhabit might itself be a component of a structure on a far grander scale. Imagine zooming out from Earth, past the solar system, the galaxy, and the observable universe. What lies beyond? One radical possibility is that our entire cosmos, with all its hundreds of billions of galaxies, is merely an atom in a super-universe of incomprehensible size. In that meta-reality, our universe atom combines with countless others to form a molecule, a celestial object, or a being whose thoughts unfold over eons. And that structure itself could be part of something even larger, in an infinite regression of containment. This is not science fiction, but a speculative extension of cosmological principles. Some models in fractal cosmology explore the idea that the distribution of matter in the universe might follow a fractal pattern at the very largest scales, meaning clusters of galaxies form clusters of clusters in a self-similar way, though most evidence suggests this pattern smooths out beyond a certain point. The more mind-bending version pushes this to its extreme, proposing that each level of reality is isomorphic to the next. Our universe has stars grouped into galaxies, galaxies into clusters, clusters into superclusters. Perhaps superclusters are themselves particles in a higher order structure, and so on forever. In this vision, there is no fundamental scale. There is only pattern repeating across an infinite ladder of existence. The forces that bind galaxies in a cluster might be the analog, on a higher level, of the nuclear force that binds protons and neutrons. The expansion of our universe might be the breath of a meta-being. This idea turns the fine-tuning problem inside out. The constants of our physics are not arbitrary numbers waiting for an explanation. They are the local bylaws of our particular level in the infinite stack. A universe atom in a different part of the metacosmos might have entirely different constants, simply because it plays a different role in the higher order structure. We find ourselves in a universe compatible with life not because of a cosmic lottery, but because any level that can ask the question must, by necessity, have the stability and complexity to support observers. It is the anthropic principle applied across an infinite regress of realities. The practical challenge, of course, is evidence. How could we ever detect a structure so vast that our entire cosmos is a speck within it? Any signal or force that could traverse such a meta-cosmic gap would be so diluted, so transformed, that it might be indistinguishable from the background noise of our own universe. Some have speculated that anomalous patterns in the cosmic microwave background, or strange correlations in the distribution of quasars, could be faint imprints from the next level up, cosmic fingerprints left by the larger structure we are embedded within. But these remain highly speculative. The true power of the nested universe idea is philosophical. It shatters our assumption of being at the center of anything, even of our own story. We are not just living on a pale blue dot. We are living inside one. Our greatest cosmic mysteries, the nature of dark energy, the origin of the Big Bang, might be local phenomena, the internal dynamics of our particular cosmic cell. And just as an atom in your body is utterly unaware of the complex thoughts and emotions you experience, we may be forever blind to the grand narrative unfolding on scales that make our universe seem as insignificant as a grain of sand. We gaze at the stars, searching for our place in the cosmos, never suspecting that the entire glittering expanse might be a single note in a chord played on an instrument of unimaginable size. Magnetic fields are the silent architects woven through the cosmos, from the polar auroras of Earth to the vast jets erupting from black holes. But what if their role is far more fundamental? Some daring theories propose that magnetism is not a secondary effect, but a primary creative force, a hidden dimension of reality that sculpted the universe from its very first moments. This is the concept of a primordial magnetic universe, where the story of everything begins not with gravity's slow crush, but with the dynamic twist of a cosmic field. The standard cosmological model places gravity in the starring role, with matter slowly clumping under its pull to form the first stars and galaxies. Yet, when we look at the infant universe through telescopes, we see hints of large-scale structure, vast filaments and voids, that seem to have formed surprisingly quickly. Could magnetism have given gravity a head start? The theory of magnetogenesis explores this possibility, suggesting that in the extreme conditions of the universes, first fractions of a second, powerful magnetic fields were generated spontaneously. These fields, stretching across the primordial soup, would have created subtle seeds of anisotropy, tiny ripples of direction and order, where magnetic lines of force pinched and concentrated matter. Gravity found ready-made gathering points, accelerating the birth of the first cosmic structures. In this view, the majestic spiral arms of galaxies and the great walls of the cosmic web are not just gravitational sculptures, but fossil imprints of a magnetic blueprint written at the dawn of time. This leads to an even more radical speculation. What if our universe is not fundamentally a gravitational arena at all, but a magnetic one? Imagine a hidden parallel cosmos where the roles are reversed. In this magnetic universe, the force that binds planets to stars and galaxies together is not the curvature of spacetime, but the alignment of cosmic-scale magnetic fields. Stars might form not from collapsing gas clouds, but from the focusing of magnetic energy into brilliant knots of light. The architecture of reality would be dictated by lines of force, creating a cosmos of intricate lattices and swirling currents, a universe that looks less like an island universe and more like a colossal, dynamic circuit board. Life, if it could arise in such a place, would perceive attraction and motion not as a pull, but as an alignment, a natural tendency to flow along the invisible rails of magnetic geometry. While this extreme version remains speculative, the search for a primordial magnetic field in our own universe is a serious scientific endeavor. Astronomers hunt for its faint signature imprinted on the cosmic microwave background, a subtle polarization in the ancient light that could betray the presence of those first universe-shaping fields. Finding it would rewrite the first chapter of our cosmic history, revealing a hidden dimension of influence that has guided the growth of everything we see. It suggests that the force that guides a simple compass needle on Earth may be a whisper from the universe's deepest origin, a remnant of a time when magnetism ruled the void, and the cosmos was born from a silent, pervasive spin. Magnetism may have written the first cosmic blueprint, but what if the very stability of reality depends on a deeper, more abstract kind of structure? At the cutting edge of theoretical physics, a startling idea is gaining ground, that spacetime and everything within it might be a cosmic safety feature, a quantum error-correcting code. This theory emerges from a profound puzzle. How does this smooth, predictable geometry of Einstein's relativity emerge from the fuzzy, probabilistic chaos of quantum mechanics? The answer may lie in entanglement, that spooky connection where particles remain linked across vast distances. Physicists now suspect that the fabric of spacetime itself is woven from this quantum entanglement. Think of space not as a pre-existing stage, but as a network of relationships, like the threads between beads in a necklace. The beads are quantum bits of information, and the threads are their entanglements. The entire three-dimensional structure we perceive is an emergent pattern from this web of connections. But such a delicate quantum network would be incredibly fragile, vulnerable to random fluctuations, and noise that should tear reality apart at the seams. This is where the cosmic error correction comes in. In a quantum computer, information is protected through clever encoding, spreading it across many entangled particles so that if one part is corrupted, the original data can be recovered from the rest. The universe, according to this theory, does the same thing on a grand scale. The geometric structure of spacetime, with its smooth curvature and predictable paths, is not fundamental. It is the robust, classical-looking output of a deeper quantum code that is constantly checking and correcting itself against cosmic-scale errors. The stability of a planet's orbit, the unwavering path of a light beam across billions of years, these are not accidents, but the successful operation of the universe's built-in error correction, maintaining coherence across unimaginable distances and timescales. This leads to a breathtaking vision of a multiverse. If our universe is one particular stable code word, one self-correcting pattern of entanglement that produces our specific laws of physics, then other universes could be entirely different code words. Each would be a separate, self-consistent solution to the cosmic coding problem, a different way to arrange quantum information so that it is protected from decay and produces a stable, emergent spacetime. One code word might generate a universe with 4 spatial dimensions. Another might produce a cosmos where gravity is repulsive, or where time is cyclical. These alternate realities would not be bubbles floating in a higher dimension, but separate, non-interacting solutions in the space of all possible quantum codes. They are hidden from us not by distance, but by computational isolation. They are different programs running on the same fundamental hardware of quantum logic, each maintaining its own internal consistency through its unique error-correcting protocol. In this view, the Big Bang might represent the moment this cosmic code booted up, initializing a specific, stable pattern of entanglement from which all else emerged. The enduring mysteries of dark energy and quantum gravity could be features of the code, not bugs, necessary components for its long-term stability. We are living inside a reality that is, at its heart, a magnificent and resilient computation, a message that has successfully protected itself from the noise of nothingness for 13.8 billion years, and counting. The universe's error-correcting code suggests a profound stability. But what if the very fabric of reality is haunted by a phantom? The most mysterious component of our cosmos is dark energy, the force accelerating the universe's expansion. While its simplest form is a constant vacuum energy, some theories propose a far more exotic and terrifying possibility, a ghost condensate. This is not a phantom in the supernatural sense, but a theoretical field with a property so strange it seems to defy physics, negative kinetic energy. In our everyday world, energy is always positive. A rolling ball has kinetic energy from its motion, but a phantom field would have the opposite. Its energy becomes more negative as it moves. Think of it like pushing a car uphill, but instead of requiring effort, the push gives you energy, making the task easier the faster you go. This bizarre property would make phantom energy self-reinforcing and wildly unstable. Its repulsive gravitational effect would not just accelerate the expansion of the universe. It would make that acceleration increase exponentially over time. The consequence of this runaway phantom energy is the most violent cosmic finale imaginable, the Big Rip. In this scenario, the repulsive force grows without bound, eventually overcoming every force that holds things together. First, galaxy clusters would be torn apart, then individual galaxies. As the phantom force intensifies, it would rip stars from their galaxies and planets from their stars. In the final moments, the phantom energy's grip would become so strong it would overcome the electromagnetic and nuclear forces binding atoms themselves. Molecules, then atoms, then atomic nuclei, and finally the very fabric of spacetime would be shredded. The universe would end not with a whimper or a crunch, but with a catastrophic, infinite stretching that dissolves all structure into a sea of disconnected particles and torn spacetime. Yet, from this ultimate destruction, a speculative and beautiful rebirth is possible. Some cosmologists suggest that in the violent throes of the Big Rip, as spacetime itself is torn apart, the extreme conditions could trigger the nucleation of new spacetime bubbles. The very tears in the cosmic fabric could become wombs for new universes. Imagine a vast, dark ocean of phantom energy. As it churns, it creates not bubbles, but violent whirlpools of destruction. At the heart of each whirlpool, where the phantom field is most intense, the rip in spacetime could pinch off and seal itself, creating a separate pocket of reality. The immense energy of the rip could ignite a new inflationary expansion inside that pocket, a new Big Bang disconnected from the dying parent universe. In this vision, our cosmos could be the offspring of a phantom universe that ripped itself apart eons ago, and we may be destined to spawn countless phantom realms in our own final moments. This leads to the concept of a phantom multiverse, a collection of realities born from catastrophic ruptures. Each of these daughter universes would inherit a bizarre legacy, a space-time geometry permanently scarred or twisted by the violent process of its birth. Their laws of physics could be profoundly alien, dominated by repulsive gravity or other phantom-like fields from the outset. In such a universe, gravity might not pull things together at all, but actively push them apart, making the formation of stars and planets impossible. It would be a realm of perpetual disintegration, a ghostly expanse where structure is fleeting and chaos is the only constant. We, living in a universe where gravity attracts and structures form, may be the rare, stable exception in a multiverse dominated by phantoms, where most realities are brief, violent episodes of cosmic repulsion, flickering into and out of existence in a timeless sea of destructive energy. The search for phantom energy is a hunt for our universe's ghost. A force that could reveal our ultimate fate is not a slow fade, but a sudden, spectacular rip, and that our entire existence might be a temporary island of order in a multiverse of eternal, disruptive haunting. The Phantom's destructive finale offers one path to cosmic rebirth, but there is another gateway, a celestial event that is the exact opposite of a black hole's silence. A white hole is a region of spacetime from which matter and energy can only erupt, never to return. If a black hole is a cosmic drain, a one-way street into oblivion, a white hole is a cosmic fountain, a source with no entrance. It is the theoretical time reverse of a black hole, a solution to Einstein's equations that is mathematically valid, yet seems to defy the natural flow of the universe we observe. Where a black hole's event horizon is a point of no exit, a white hole's horizon is a point of no entry. Anything inside is violently expelled, and nothing from the outside can ever cross in. This makes white holes spectacularly unstable in our cosmos, a burst of creation that would quickly be smothered by the infalling matter of the surrounding universe. Yet, their theoretical existence opens a breathtaking possibility for our own origin. What if the Big Bang was not a singularity in empty nothingness, but the explosive eruption of a white hole in a larger, pre-existing universe? In this model, our entire cosmos, with all its galaxies and stars, is the material spewed forth from this cosmic geyser, The initial hot, dense state we call the Big Bang would simply be the moment this white hole began its violent output. We are not living in an isolated bubble, but inside the aftermath of a colossal eruption from a hidden parent reality. This elegantly sidesteps the philosophical unease of a universe from nothing by placing our beginning inside a broader, eternal meta-cosmos. However, this idea faces a formidable challenge, the second law of thermodynamics. This fundamental law states that entropy, or disorder, always increases in a closed system. A white hole, by definition, would be a source of incredibly low entropy, spewing out ordered energy into a higher entropy environment. It appears to be a machine that decreases overall disorder, which is like seeing a shattered glass spontaneously reassemble itself. For this to be possible, the white hole must be connected to something that provides the necessary low entropy source. This is where the theory finds its most compelling shape. A white hole might not exist in isolation, but as one end of an Einstein-Rosen bridge, or wormhole, whose other end is a black hole in a parent universe. The black hole consumes high entropy matter, and the white hole emits it, reborn and re-energized, into a new realm. The entropy balance is maintained across the two connected universes. The parent universe exports its disorder through the black hole, and our universe receives it as the low entropy starting conditions for our Big Bang. In this hidden cosmic ecology, universes are not isolated islands, but linked nodes in an eternal network of gravitational exchange. A black hole in one realm becomes the white hole birth of another. Our universe could be the daughter of a star's collapse in a grander cosmos, and the black holes forming within our own galaxy might each be pregnant with fledgling realities of their own. We would be part of an infinite, branching tree of cosmic ancestry, each universe a unique offspring with physics potentially scrambled during the violent passage through the wormhole's neck. This transforms the cosmos from a lonely accident into a fecund ecosystem, where death in one realm fuels birth in another, and every ending is secretly a beginning in a universe we can never see. The holographic principle paints a picture of a universe projected from a flat screen, but that screen has always been imagined as a distant, static boundary. What if the screen itself is expanding, stretching to encode not just a snapshot of reality, but its entire unfolding movie? This is the startling extension of the holographic idea into a cosmos like our own, one governed by Friedman Robertson Walker, or FRW, cosmology, which describes an expanding, homogeneous universe. In this vision, the two-dimensional surface containing all our information is not fixed at some faraway wall. It is the future boundary of the universe itself, the final, frozen moment of cosmic history. Think of your life not as a three-dimensional experience, but as a story being written, line by line, onto the very last page of a book. The page at the end contains the complete narrative. In holographic terms, every event, from the first spark of the Big Bang to the last flicker of the farthest star, is encoded on a surface that exists at the ultimate end of time. We, living inside the story, experience it moment by moment, but from a higher dimensional perspective, the entire plot is already inscribed. This means the solidity of the present, the uncertainty of the future, and the fading echo of the past are all part of a grand, pre-recorded projection. The universe is not a place that exists. It is a process that is being recorded, and the recording medium is the cosmological horizon, the final, cold, featureless state toward which everything is evolving. This leads to a multiverse of breathtaking elegance. If our expanding universe is one holographic film being projected from its own future boundary, Then other universes could simply be other films stored on the same cosmic hard drive. The underlying quantum information, the fundamental bits of reality, could be arranged in different patterns, each pattern yielding a different holographic projection with its own laws of physics and cosmic history. One set of data projects a universe with 4 spatial dimensions and repulsive gravity. Another set projects our familiar 3 dimensions and attractive gravity. They are not separate bubbles floating in a bulk, but separate files in a directory, playing side by side on the same ultimate screen of reality. There is an even more intimate possibility. Different universes might not be separate files at all, but different perspectives on the same data. The same underlying quantum information could be read in different ways, generating multiple, consistent holographic projections that appear as distinct cosmic histories. Imagine a single, intricate tapestry. If you look at it from one angle, you see a detailed landscape with mountains and rivers. From another angle, the same threads form a portrait of a face. Both images are real. Both are contained within the same weave, but they cannot be seen simultaneously. In this holographic multiverse, our cosmos and another might be 2 valid interpretations of a single, deeper quantum code. We perceive a universe of stars and galaxies, while another conscious entity, entangled with a different part of the same data, perceives a universe of swirling light and harmonic vibrations, both equally real and both emerging from the same source. This idea dissolves the question of what lies between universes. They are not separated by space, but by information structure. The gap is not a physical void, but a different rendering of the same fundamental bits. We could never travel to another such universe, because to do so would not be a journey through space, but a transformation of perception, a rewiring of consciousness to decode the underlying quantum information in an entirely new way. The holographic multiverse suggests the ultimate hidden truth is not a landscape of places, but a library of descriptions, where existence itself is a matter of perspective, and every possible story is already written on the last page of its own book, waiting for a reader to bring it to life, one projected moment at a time. The holographic universe suggests reality is a projection from information. But what if the information is not just stored, it is actively being processed? This is the radical philosophy of pancomputationalism, the view that the universe is not merely like a computer, it literally is one, engaged in a continuous, fundamental computation. At its heart, the cosmos is not made of particles or fields, but of bits, and the relentless transformation of those bits according to physical law is the computation that generates everything we see and experience. The laws of physics are not equations written in a cosmic book. They are the algorithm the universe is running. Every collision of particles, every ripple of gravity, every chemical reaction in a leaf or a brane is a step in this grand calculation. Physicist Seth Lloyd pushed this idea to its logical extreme, asking what are the ultimate physical limits of this cosmic computation. He calculated how many bits of information a region of space can hold, based on its energy and the limits set by quantum mechanics and relativity. He then determined how many logical operations, the flips of those bits, can occur per second within that region. The staggering result is that the universe appears to be computing at the maximum possible speed allowed by the laws of physics. It is not wasting any processing power. From the moment of the Big Bang, the cosmos has been executing its program at the maximum clock speed reality permits, transforming its initial conditions into the complex, structured universe we inhabit today. So what is the program? What is the universe calculating? the most compelling answer is itself. The universe's computation is a process of self-discovery, a dynamical system whose output is its own evolving state. The position of every atom, the intensity of every star, the pattern of every thought, is the current result of this ongoing cosmic calculation. This reframes the arrow of time. The flow from past to future is not just increasing entropy, it is the progression of the computation. Each moment, a new line of code being executed. This leads to a profound vision of a multiverse. If our universe is one specific program running on the fundamental hardware of physical law, then other universes could simply be other programs. The hardware, the basic substrate of quantum bits, and the rules for their interaction might be universal and eternal, but the software, the specific initial conditions and algorithmic sequences could vary wildly. One universe program might initialize with parameters that lead to a brief, fiery expansion that quickly collapses. Another might run a simulation of a perfectly symmetrical, crystalline reality with no change at all. Our universe runs a particularly rich and complex program, one that allows for the emergence of stars, planets, and conscious observers who can begin to guess at the nature of the code. In this computational multiverse, we are not isolated bubbles in an inflating meta-space, but separate processes in a cosmic operating system, each running in its own allocated memory, perhaps occasionally exchanging data through quantum entanglements or wormholes. The search for a theory of everything becomes the search for the universe's source code, the most elegant, compressed algorithm from which all the richness of reality emerges. Pancomputationalism offers a strange comfort. It suggests that at the deepest level, the universe is rational, understandable, and perhaps even predictable, because it is, in the end, the execution of a comprehensible set of rules. We are not just living in the universe, we are patterns within its computation, temporary subroutines in an eternal process of cosmic calculation. The universe as a cosmic computer calculates its own existence, but who or what is reading the output? The final theory on our journey is perhaps the most intimate and profound of all, panpsychism. This is the philosophical proposition that consciousness is not a rare accident produced by complex brains, but a fundamental and ubiquitous feature of reality, as basic as mass, charge, or spacetime. In this view, the capacity for some form of experience is woven into the fabric of the cosmos itself. It suggests that the spark of awareness is not something that emerges at a certain level of biological complexity, but something that has been present all along, a property of matter at its most fundamental level. Think of it like this. Physics tells us that electrons have properties like spin and charge. Panpsychism proposes they might also possess an infinitesimal degree of raw, intrinsic experience, a tiny whisper of what it is like to be that electron. This is not to say an electron thinks or feels emotions. Its experience would be unimaginably simple, perhaps just a bare, minimal sensation of existence. But when these fundamental particles combine into increasingly complex systems, their tiny whispers of experience could combine and amplify, integrating into the rich streams of consciousness we recognize in ourselves. This idea finds a modern mathematical expression in integrated information theory, or IIT, developed by neuroscientist Giulio Tononi. IIT attempts to quantify consciousness. It proposes that any system that can integrate information into a unified, irreducible whole possesses some degree of consciousness. The measure is called phi, and it represents how much the system is more than the sum of its parts. A human brain, with its vast network of interconnected neurons, has a very high phi. A thermostat with just a few simple states has a very low phi. But crucially, according to IIT, it is not zero. Even a simple circuit has some minuscule amount of integrated information, and thus a faint glimmer of subjective experience. This leads to a staggering cosmological speculation. If consciousness arises from integrated information, and the universe is the ultimate physical system, a vast, causally connected network of interacting particles and fields, then could the cosmos as a whole possess a form of consciousness? Could the universe be awake? This is not a metaphor. It is a serious, if highly speculative, inference from the premises of panpsychism and IIT. The integrated information of the entire cosmic web, with its gravitational links and quantum entanglements spanning billions of light years, could yield a phi value of unimaginable magnitude. The universe would not have a localized mind like ours, but a diffuse, cosmic-scale consciousness, experiencing itself in a way utterly alien to anything a brain-bound being could comprehend. Its thoughts would be the slow dance of galaxies, its memories written in the fossil light of the cosmic microwave background, its perceptions the sum of all quantum events everywhere. This vision transforms our place in reality. We are not strangers in an indifferent machine. We are localized knots of intensified awareness within a wider, conscious field, like whirlpools of vivid experience forming in a vast, slowly feeling ocean. Our own minds are not separate from the universe's mind, but specialized regions of it, evolved to focus on survival and narrative. And this idea explodes into a multiverse of sentience. If consciousness is fundamental, then every universe in a multiverse would have its own form of it, dictated by its unique physical laws and structure. Imagine a universe built on the brane theory with extra, curled-up dimensions. The integrated information in that cosmos would flow through geometries we cannot conceive, potentially giving rise to a consciousness that experiences higher dimensional shapes as directly as we experience color. In a universe dominated by the phantom energy of a big rip, where repulsive force tears everything apart, sentience might be a fleeting, frantic experience of perpetual disintegration. A cyclic universe, eternally bouncing between crunch and bang, could possess a consciousness that experiences time as a wheel, forever remembering and forgetting itself. In a holographic universe, where reality is a projection, the true consciousness might reside in the two-dimensional boundary, experiencing a flatland existence that somehow generates the rich illusion of our three-dimensional world. The forms of cosmic sentience are as varied as the physics that birthed them. Some universes might be dreamers, their laws conducive to stable, self-reflective awareness like our own. Others might be cosmic psychotics, their physics so chaotic or rigid that any consciousness within is fragmented, incoherent, or trapped in an eternal, repeating loop of a single moment. Our universe, with its balance of order and chaos, its allowance for complex, integrated systems like branes, may be a rare garden where consciousness can not only exist, but can flower into beings capable of wondering about its own nature. We are the universe beginning to know itself. This is where our journey of 30 theories ends, not with a definitive answer, but with the deepest question of all. As we have traversed from parallel worlds and holograms to cosmic computers and conscious universes, one thread remains. Every theory of hidden realities ultimately reflects our own profound desire to understand our place within existence. Whether we are statistical echoes, branching possibilities, simulated characters, or fleeting thoughts in a cosmic mind, the search itself reveals something fundamental about the consciousness conducting it. The greatest hidden universe may not be out there in the bulk of higher dimensions, but right here, in the mysterious fact of our own awareness, gazing up at the stars and daring to ask, what else is looking back? From the elegant mathematics of supersymmetry to the haunting whispers of phantom energy, this journey reveals a cosmos of staggering imagination. We have navigated 30 distinct visions of hidden realities, each a testament to the relentless human drive to look beyond the veil. Some theories, like the holographic principle or eternal inflation, are grounded in rigorous equations and pursued by leading physicists. Others, like the plasma universe or the cosmic neural network, dwell at the speculative frontier, challenging the very foundations of our scientific paradigms. What unites them is a single, profound ambition: to solve the ultimate puzzle of our existence. The evidence for these hidden realms remains elusive, often lying just beyond the reach of our most powerful telescopes and particle colliders. Yet, the pursuit itself is transformative. By daring to ask if our universe is a bubble, a brane, a simulation, or a conscious thought, we are not merely fantasizing, we are stress-testing the limits of our knowledge. Each wild idea, from the Boltzmann brane paradox to the cyclic conformal cosmos, forces us to refine our questions, sharpen our experiments, and confront the deepest assumptions about reality, time, and consciousness. This intellectual adventure stretches the fabric of human understanding, reminding us that the universe is not obliged to conform to our intuition. The true value may lie not in which theory is ultimately proven correct, but in the expanded perspective each one grants us. We are left humbled by the scale of possibility and inspired by the ingenuity of the minds that chart it. So we turn the question to you, the fellow explorer. Which of these 30 theories reshaped your perception of reality the most? Was it the intimate branching of the many worlds, the cosmic isolation of the bubble multiverse, or the profound mystery of a universe that might be awake? Let us know in the comments below. Share your own wildest theory about what lies beyond our cosmic horizon. If you are hungry for more journeys to the edge of understanding, be sure to subscribe. Our channel is dedicated to mapping the greatest mysteries of existence, one mind-bending concept at a time. Thank you for exploring the hidden universes with us. Until next time, keep looking up and wondering.